One of the things we never do when we're working polyprotic acid problems is make it practical for you so you can appreciate what kind of problem you're working. So I'm going to write down some compounds here with their concentrations. And I want you to be able to figure out what equilibrium constant these things are associated with. So there's 5 compounds. What am I going to do with them? Well, I'm going to do with them what you do with any acid-base problems you work. I'm going to get rid of the spectator ions. You get rid of the spectator ions and things become abundantly clear. So there are 2 lithium ions there. This is one of the tricky things about polyprotic acids is you see Li2 and you think that's something special. That's just 2 lithiums. That's just 2 Li pluses. So when I get rid of those 2, that makes a double minus here. Right down here is LiHCO3. I get rid of one of these, and there's a single minus. There's an Li and an Na. This one here gets rid of 1 positive. This one gets rid of a second positive, so I've got 2 negatives to counter it. This one right here, I'm getting rid of 3 positive charges, so this is minus 3. I have phosphoric acid, carbonate ion, bicarbonate ion, a biphosphate species, and a phosphate species. Take each of those CO3s or PO4s and make them into an A. And let's see what we've got. There is H3A. There is A minus 2. There is HA minus. My goodness, this is suddenly looking really clear, isn't it? These compounds that were kind of bizarre looking before are now these compounds here. And when I'm thinking about what kinds of equilibrium problems to work, what my Ka1, Ka2, Ka3 should be, this is going to tell me the answer. Because if I'm seeing Li2KPO4, I'm not immediately thinking A minus 3, oh, that's a Ka3 problem. But I would think that if I had converted this into this set of problems here, nice standard using A as your format, number of protons in front, charge behind, and then I compared it to either the diprotic or the triprotic case. H3A is the most acidic species. There it is, and the Ka1 describes its dissociation. A minus 2 is the one missing all of its protons. It's the most basic species, and it's diprotic. It's this one right here. And Ka2 describes its dissociation. HA minus is a diprotic system. That's this one sitting here. Oh my goodness, this is kind of interesting. It can either go this way and make H2A. It can go this way and make A minus 2. Evidently, both of those K values seem to matter. And sure enough, we're going to see how that plays out in just a second. There's HA minus 2, this guy right here, which can go this way to make Ka2 or this way to make Ka3. And there's A minus 3 right down there with this Ka3 staring me in the face. Now, at this point, you're probably saying, well, you're showing me a lot of acids, but I feel kind of basic-centric today. Why is everything written in terms of an acid? That may be an acid, but that's a base. If that's got Kas, doesn't that have Kbs? And the answer is it sure does. There is a Kb1 for the adding of a proton. There is a Kb2 for the adding of a proton. Heck, there are 3 Kbs here, Kb1, Kb2, and Kb3. How do I find them? Well, it's not that hard to find them. Kbs and Kas added together have to equal 14. So when I show you that the Ka2 here is 10, you know that the Kb1 is 4. If the Ka1 is 4 here, then the Kb is 10 for this. That's a Kb of 12, a Kb of 7, a Kb of 1.5, a Kb of 12, a Kb of 5, a Kb of 4. I could rewrite every bit of this, but I won't put you through it, so that this was written not as a collection of acid dissociations, but it could have been written in the opposite direction as adding protons to bases. This will come up in a little bit as I show you how to work weak base problems involving polyprotic acids. But for right now, we'll just leave it looking in a very acid-centric sort of way. Don't forget, though, that there was a time when if I showed you a Ka and asked you what the Kb was, you would have done it like that. Well, nothing stops you from doing that here either.